Hello good folk. Today we introduce ourselves to a new topic called universal gravitation. To kick things off, first of all, we ask ourselves, what is it that keeps all of the planets in order around the sun in specific orbits? Well, that answer most of us know to be gravity. There is a force of gravity that exists between the sun and each of these planets, which keeps them in fixed orbits around the sun. However, so far we have only talked about gravity near the surface of the earth, right? We have talked about objects with mass having a weight due to Earth's gravitational attraction. However, how does it work in space? How does the sun exert a gravitational force on any other planet? That answer we haven't discussed in detail. Let's go ahead and discuss now by looking at an example. Earth's orbit around the sun is nearly circular, with radius 1.5 times 10 to the 11 meters. What is the force that holds the Earth in orbit around the sun? Mass of the Earth is given to be 5.97 times 10 to the 24 kilograms. Whenever I see this number from a very early age, when I started studying physics, I would ask myself, how do you actually weigh the Earth? Is there a scale big enough that someone goes up and holds the Earth and just puts it on a scale? Of course, that's nonsense. Think about it. How does people come up with this number, right? That's an interesting thing to think about. Anyways, let's move on to our problem. And this is a very simple visualization of the Earth going around the sun in its nearly perfect circle, and my ability to draw a circle is also nearly as good. The main goal of this problem would be to find the force that holds the Earth around the orbit. So we want to find this force of gravity that the sun exerts on the Earth to hold it in orbit. Since this is a circular orbit, by now we should be realizing that we can apply our knowledge of circular motion. What do we know from circular motion? We know that for circular motion, Newton's law changes as the summation of forces, or the resultant force in any specific direction, is equal to the mass of the object times the acceleration in that direction. The acceleration in a circular motion is towards the center, the centripetal acceleration, and we know this to be defined as the magnitude to be v squared, that is the speed of the object squared, over r, which is the radius of the circle it's moving on. Do we know most of the things? We know the mass of the Earth, which is going around in a circle around the sun, so we know this quantity, and we know that the radius of this orbit, this distance, let's call it r, is 1.5 times 10 to the 11 meters. So we know this. What to do about this v? Well, this v is the speed of the Earth. Right? And since Earth makes a full rotation around the sun in 365 days, that means over a long period of time of 365 days, it covers this whole distance. So at any specific point in time, the speed of the Earth would be constant. Hence, we can use our concept of average velocity, or our equation for average velocity, to find the speed. Average velocity is distance over time, right? And you may ask then, if the speed of the Earth is constant, how are we applying Newton's second law? Because we know that if speed were constant, the acceleration would usually be 0. However, remember that this is a centripetal acceleration. The velocity would be tangential to the circle, and this may be a constant speed. However, the velocity isn't constant, since the Earth or anything moving in a circle is always changing direction. Therefore, we have the centripetal acceleration. Moving on, what is the distance covered by the Earth? Well, since it's moving on a circle, meaning distance is nothing but the circumference of that circle, 2 pi r, right? And this time would be that time for 1 year it takes to complete one full revolution, which is 365 days. Okay, so first of all, we want everything in meters. This is already in meters because r is given in meters, so this thing is okay, it's in meters. And 365 days is not an SI unit, so we want the days to be converted to seconds. What this comes out to be, the speed of the Earth to cover the full distance, to cover one full rotation, is 2.99 times 10 to the 4 meters per second. Now we wanted to find this force of gravity, Fg, right, is equal what? To find any force, first of all, what we do? We draw the free body diagram. Let's say that the Earth is here, the Sun is here. We draw the free body diagram for the Earth. Earth, the only force acting on it would be towards the center, because towards the center is the Sun, which is attracting the Earth, and the Earth only has centripetal acceleration. Hence, the only force should also be a centripetal force, and this force is the force of gravity exerted on Earth by the Sun. Therefore, we can write, we also choose this direction to be positive x and write the Newton's second law equation as follows. Fg is the summation of all the forces in this x direction equal to mass of Earth times v squared over r. V squared is 2.99 times 10 to the 4 squared over r. R is 1.5 times 10 to the 11. If you do this, you get the force of gravity as 3.56 times 10 to the 22 newtons. This is the force of gravity which the Sun exerts on the Earth to keep it in a circle. Now, two important things to note about this. First of all, we have already talked about Newton's third law. What does that say? Every force will have a reaction force to it. So if Sun is exerting a gravitational force of this much newtons on Earth, the Earth must also be exerting the same magnitude of the gravitational force on the Sun. So in other words, not only is the Sun attracting the Earth is also attracting the Sun. So there is a mutual attraction between these two massive bodies, and it is a general rule. Anywhere in the universe, wherever you find any two massive objects, there will be gravitational force between them. Okay, so that is why this whole chapter is given the name as universal gravitation, because it works anywhere in the universe, and anywhere in the universe, wherever you have two masses, they attract each other with the force of gravity. Second thing to notice is that my free body diagram looks like that the gravitational force is now acting horizontally. Well, we have always learned gravitational forces till now being a vertical force. However, that force was only near the surface of the Earth. This is universal gravitation. This is more of a force that causes things to move in a circle, this specific force. So, at any point in the circle, no matter if it's a horizontally displaced, the Sun and Earth, the force will be directed towards the Sun, and if it's at this point, the force will be vertically downwards directed to the Sun. Regardless of your position, of the Earth's position, the force will always be pointed towards the center. Okay, so that is the two things that we wanted to notice about this problem. Carrying on from the example that we have just seen, let's ask ourselves if this formula for weight that we have been doing thus far, does this still work when we are talking about planets or anywhere outside the Earth? Well, no, because g, the acceleration due to gravity that we have been using as 9.8, it is only valid near the surface of the earth. It is not known universally, and so we cannot use this naive formula for weight anywhere in the universe. This is only valid for situations near the surface of the earth or other planets where we know what the value of g is. As a solution to this conundrum, Newton came up with his law of universal gravitation. This works universally, right? And mathematically it reads Fg is equal to g times m1 times m2 over r squared. G is the gravitational constant, which is a constant number also called Newton's constant of 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. As we can see, this is a very small number. M1 is the mass of object 1, M2 is the mass of object 2, R is the center to center separation of mass 1 and mass 2. Let's talk about this a little bit more. What does this actually tell us? It tells us that any two masses in the universe, any two, it doesn't have to be two planets, it can be two stones. Any two masses will exert gravitational forces on each other, and that magnitude of that gravitational force is directly related to the product of their masses. So if this product is higher, the force is greater, and inversely related to the center to center separation of the two masses. So the further you move them apart, further you move M1 and M2, the two masses apart, the smaller the gravitational force becomes between them. This G, the gravitational constant or Newton's constant, basically tells us how strong a force gravity is. Now, there are four fundamental forces in nature that we can observe. One is gravity, two is electromagnetic force, three is strong nuclear force, and four is weak nuclear force. Gravity turns out to be the weakest of the four forces. Why? This gives us an indication. The strength of gravity can be summed up by looking at this number, and we can see this is a very small number, 10 to the minus 11. So gravity is actually a very weak force. Let's look at an example to investigate the idea behind Newton's law of universal gravitation. Here we have the International Space Station, or ISS for short, circling around the Earth, and it's a circular orbit with an orbit radius of r, small r, which is equal to 400 kilometers, and the radius of the Earth is given to us to be 6.37 times 10 to the 6 meters. Inside the ISS we have an astronaut whose mass is said to be 75 kilograms. We want to know what is the force of gravity that the Earth exerts on the astronaut. Okay? First of all, let's make some assumptions, and in physics we often make assumptions to make our lives easier since we are not smart enough. Many physicists would differ, but I'm not one of those many physicists. The assumptions are: consider the astronaut and ISS to be the same object. Why is it sensible to do so? Because compared to the Earth, with respect to the Earth, the size of the ISS and the size of the astronaut that we are looking at inside the ISS is very negligible. So it would be plausible to consider them to be one object. So astronaut plus ISS is the same object. So if we say that the Earth is separated by a distance r of ISS, then we are also essentially saying that the Earth is separated by the same distance from the astronaut. Okay? Now let's move on and try and solve this problem. What do we know? We know Newton's law for universal gravitation, which would give us the magnitude of the force of gravity that keeps the space station in orbit around the Earth. Fg is equal to gravitation constant g times mass of the Earth me times mass of the astronaut, let's call it AST, MAST, over r squared. We know g, we know me, the mass of the Earth, we know the astronaut's mass, but this is the tricky part. What is this r? As we have mentioned before, it is the center to center separation of the two objects that we are looking at. Here we are looking at Earth and the ISS. So in fact, if we use r, capital R, to be equal to the small r, that wouldn't be correct, because small r is the separation distance of the Earth's surface to ISS and the astronaut. But we want to put in here the center to center distance, or the center to center separation between the two objects. So from the Earth's center, we have the radius of the Earth that reaches the surface of the Earth, and from the surface of the Earth we have the orbit radius, small r. So in fact, capital R is addition of the radius of the Earth plus the orbit radius, small r. Okay, so in fact we end up with gravitation constant is 6.67 times 10 to the minus 11 times mass of the Earth is 5.97 times 10 to the 24 kilograms. Mass of the astronaut is 75 kilograms over radius of the Earth, which is 6.37 times 10 to the 6 plus orbit radius, which is 400 kilometers. So 400 times 10 to the 3 meters. Remember, we are always going to solve things finally in SI units. This gives us a force of gravity equal to 652 newtons. This is the force of gravity that the Earth exerts on the ISS to keep it in orbit. Conversely, this is also the force, but in the opposite direction, that the ISS exerts on the Earth. Now, let's move on to part 2 of the same question. This asks, how fast is the ISS moving? How fast is the International Space Station moving? In other words, also this means, because of our assumption, how fast is the astronaut moving? Since we only know information about the mass of the astronaut, we will use the mass for the astronaut inside the ISS even when we are considering the ISS to be moving, because we have assumed that ISS and the astronaut is the same object. Okay, so how do we solve this? Well, remembering circular motion tells me that magnitude of a centripetal acceleration, AC, is v squared over r. Does it apply here? Of course it does, because ISS is moving around in a circle around the Earth. So this gives me Newton's law as summation of F equals ma. A is the centripetal acceleration, which is mv squared over r. So we can somehow use this concept to find our speed. So we know that the only force that this ISS is feeling is the gravitational force that we have just calculated, and it is always directed towards the center, that is in this case towards Earth. So this summation of F becomes F of g, Fg equals to, what is this mass? This is the mass of the object that is moving in the circle, okay, that is moving around the center. In this case, this is the mass of the astronaut. Okay, so that is 75 kilograms times v squared. Remember, how fast means we are looking for speed, which is v, over r. Now, what is this r? Again, this is actually capital R, the center to center distance between the Earth and the ISS. Why? Because the force that we have calculated, gravitational force, was dictated by universal gravitational law, and that demanded that the separation distance be a center to center distance. So to use this gravitational force, we have to use the center to center distance of the two objects, which again is capital R, and we know what that is from our previous calculation. It is nothing but the radius of the Earth added to the orbital radius. Now we solve for v squared, so cross multiply fg to re plus r equals 75 times v squared. Divide both sides by 75 and we get 1 here, and then square root both sides so that we are only left with v. Okay, this comes out to be 7670 meters per second. This is how fast the astronaut or the ISS is moving in the circle. So this is the tangential speed of this ISS station and also of the astronaut. To close off this lecture on universal gravitation, we ask ourselves a final question. Does universal gravitation work on objects that are at the surface or near the surface of the Earth? Is the gravity that we feel the same gravity that the planets feel from the sun and the sun feels from the planet? The answer is yes, it does work on objects near the surface or at the surface, and it is the same gravity that acts between planets and sun and us and the Earth. Let's find out how. We know that Newton's law of gravitation states the gravitational force is equal to the gravitational constant times the mass of one object. In this case, let's call this mass of the Earth, times m. This is the mass of an object, any object that's near the surface of the Earth, over the radius of the Earth squared. Why is it the radius of the Earth? Well, if this is Earth, from the center to the surface, the distance is the radius of the Earth, and we are considering an object at the surface. So the center to center distance is just the radius of the Earth in this case, right? Anywhere on the Earth, this part of the expression is the same. Why? Because g is a constant. me, mass of the Earth, doesn't change if you go from here to here, and radius of the Earth is also constant. So this value is constant. What is this value? Let's find out. G is 6.67 times 10 to the negative 11 times mass of the Earth is 5.97 times 10 to the 24 kilograms over radius of the Earth squared. Radius is 6.37 times 10 to the 6 meters squared. If you do the calculation, this comes out to be 9.8 meters per second squared. So if you put in the units of all these different numbers, this has a units of Newton meter squared over kilogram squared, and this has units of kilograms. This will have units of meters times meters, meter squared. If you work out the units and the numbers, you would find that you end up with 9.8 meters per second squared. This is nothing but g that we have been using to find weight for objects near the surface of the Earth. Therefore, for objects near the surface of the Earth, force of gravity becomes the mass of the object, m, times this thing, which actually on Earth is 9.8. So we have seen that the gravity we feel and the gravity the planets feel, they're the same, just looked at differently. I hope this whole lecture made some sense.